Alrighty, 713, pH and solubility. Colored writing tools would be helpful for these drawings. Okay, so pH, we're usually talking about how acidic or basic something is. As a reminder, if you have less than 7, it's acidic. If you have more than 7, then it's basic. That's from, I don't remember what unit. Whatever unit, I don't know. Units blend together after a while. So, whatever unit that's from. And so, we're looking at how acid will affect solubility. So, looking at a salt, we can see the amount dissolved will depend on pH because you have the anion of the weak acid or the base depending on what is being dissolved. And so, you don't need to do the calculations for these, but you could. But then, you don't have to. And so, there's various things can affect the solubility a lot for these things. So obviously we talked about common ion in the previous section. And then this case, we're talking about pH of a solution. In future classes, potentially in college, you might talk about complexing agents, but that is not going to be covered in this class. So you can learn about that in a future chemistry course. And so salt's solubility, as it says here, is pH sensitive when you have an ion that is a weak acid or base, and constituent being made there, right? And so we're going to use Le Chat to qualitatively talk about this, okay? So here's an example with magnesium hydroxide. So we have a solid dissolving in solution, in our water. And so, we talk about how in Le Chat that if we remove something, the reaction is, or not the reaction, this process is going to compensate for that. And so when I'm talking about shifting to the right, we're going to make more product means I'm increasing the forward rate. And so because of that, more of the magnesium hydroxide solid will dissolve. And so that means I increase the solubility of the amount of salt that can dissolve. Because if I somehow removed that hydroxide, that means I needed to dissolve more in order to get more hydroxide once again so that I can, the system can reach equilibrium. And so we're going to increase the concentration of those ions. And so how can we remove OH? So one way to do that is by adding a acid to this neutral or currently this process of dissolving magnesium hydroxide. And so as a reminder, if I add an acid, that is an H+, technically, a hydronium, but we're just simplifying it here. And so because I have the H+, it can interact with the hydroxide ion and you're making water. And so technically, that is a system within itself in equilibrium. And so as I add more H+, as pH increases, the amount concentration of the H+ increases, right? And so the solubility of this salt is increasing because you need to increase the hydroxide concentration based off the KSP value. So again, if I decrease that pH by adding acid into it, because remember, a lower pH means more acidic. That means that I'm using that, or the system rather, is using that H+ to interact with the hydroxide so that you are using up the hydroxide and so you're dissolving more of the salt and so you're going to compensate for that loss of hydroxide from earlier. Okay. And so the solubility of a basic anion increases in the solution as the solution becomes more acidic, aka the pH is decreasing. So that's just basically what I said earlier. Okay, another example. So here's lead 2 fluoride. So again, we have the process of dissolving it. And so if I removed F-, we're going to shift that equilibrium to the right, aka we're increasing the forward rate, aka we're making products. And so the lead 2 fluoride is going to increase in solubility according to whatever its KSB value is, because if I got rid of some of the ion, that means I need to compensate for that ion. Okay, and so how can I remove that fluoride ion? So we know that the fluoride ion is a conjugate base to a weak acid. So if I add H plus into it, I can make this weak acid. Now, I want you to digest that, which is why I took a quick pause. So, weak acids, right? As a reminder, weak acids don't like to be its ion forms that much. A strong acid loves being in its ion form. So one of our strong acids being hydrochloric acid, right? HCl. And so if I have a strong acid, they generally will want to stay in ion form. So they'll stay mostly as H plus and Cl minus ions. And so if I add an acid to this, like a strong acid, that means that the H plus and the F minus can interact to make the HF, which is a weak acid. And so this equilibrium process, as I written here, means it will stay mostly as HF rather than the two ions separately. So again, F minus from earlier, so this is the earlier, process here is here. And so again, F minus is a conjugate base because I can grab an H, or the F minus can grab that H to become HF. And so that's why it is interacting with the H plus if it's in that solution. So just to show the overall reaction of what's happening here, like adding all this up, I essentially increased the H plus in this system. And so when I added H plus to it, the HF is interacting more. And so it's becoming HF. So you have a weak acid. And so I can dissolve more of that lead in order to, compensate for the equilibrium being messed up. So let's represent this with diagrams. And so this is where the colors come in. So I have a light color yellow here. And then I have my blue colored fluoride ions. And so at equilibrium, you have some solid, you got some of the ions. Hurrah! As a reminder, this is ionic, so technically it's 3D. So it would look something like this or something else, but similar enough, right? But we're drawing in 2D, so I have all my dots. And so, again, F minus is the conjugate base of a weak acid. In this case, HF is your weak acid. And so I'm going to add some H plus. And so because I add H plus, a strong acid, into it, then that means they're going to bond together to make the weak acid. And so here, I added an H plus. Okay, it's this pink little guy. And so when I add that H plus, the H plus, you are making this HF here. So you see how they interacted? And so it removed one of those F minuses to now become HF. So we're not at equilibrium anymore. And so more of this lead fluoride here, lead 2 fluoride, is going to dissolve. And so I add another H plus, boom. And so then more of it is dissolving. So you can see the pattern is the same approximately, but now more of it is dissolving. So I just took some from the top and then started dissolving it more. So if I add more and more acid, it's going to interact with those F minus, the fluoride ions more. See? So diagram helps a lot. You might be tested on drawing a diagram, so make sure you can. And so just to repeat this one more time, the solubility is increasing when the pH is decreasing, because when I add a H plus, it is going to interact with the F minus ions and therefore make the weak acid HF. Cool? Cool. Okay. So the F minus concentration is decreasing from when I added the H plus, And so because I added the H plus, then the salt needs to dissolve more. And so I'm going to reach whatever the equilibrium is when or when the system rather increases the lead 2 ions. Okay. So here's an example where this doesn't work. And then third example, PbCl2. So here is my dissolving of this, right? And so I need to think about what I can do to try to make this dissolve more. Now, chloride ion is the conjugate base of a strong acid. As a reminder, strong acid, make sure you know your list. And so the strong acid, HCl, is the strong guy. And as a reminder, the strong acid as a compound doesn't really exist because pretty much all of it dissociates completely. So here is what I'm talking about. If I added some H plus in there from some other strong acid, the H plus and the Cl minus are not going to really interact to make hydrochloric acid. So that's why this is not going to actually happen, this process. And so here is an example drawing it where I have my lead 2 and my chlorides. And so if I add some H plus in pink, they are not interacting with the chloride because, again, it's a conjugate base of a strong acid. Strong acids don't want to combine. Cool. So the solubility of a salt with a conjugate base of a strong acid does not get affected by pH. So it honestly depends on who the conjugate is. Okay, so things to keep in mind. One thing to keep in mind is your solubility rule you had to memorize. All sodium, potassium, ammonium, and nitrate salts are soluble in water. So, the other thing to keep in mind is strong acids. And so, as a reminder, these are, for the solubility rule you had to memorize, these 4 are soluble in water. So, since they're always soluble in water, they're always going to be in solution. They're not necessarily going to interact to make an acid. So, for example, nitrate. Nitrate is NO3 minus 1. So if you try to get rid of some of the nitrate by adding a strong acid to it, well, HNO3 is a strong acid, nitric acid. Too strong. So it's not going to happen. So like I said out loud, the example is nitrates are always soluble, so they're always in solution. And so the NO3 minus will not react with the H plus to form HNO3 because it is always soluble. If it's always soluble, that means that even if it's interacting with H, it's not going to, make that compound because, again, it is soluble. It wants to stay in ion form. Okay. Here's a quick your turn. So I have these various things in solution. And so you're seeing what happens to the solubility of each substance as you change it by putting it in, or putting acid in it. And explain why briefly. So look these over. Know your strong acid. What constitutes as an acid even. And so try this out. Pause. And we'll go over it in a second. Ready? Beep. Beep. Do I have anything to add to this other than what's on the screen? Not really. So, look these over. If you have questions, make sure to ask on Discord. Okay, bye!